All right, now the intention of today's consultation session is really to clear up any doubts you have about QA. And at the end of today, you should know how to approach one of those flowchart questions in QA, which is typically how it's tested in combined science, less so in pure science. All right. But nonetheless, QA is important, both for practical and theory. All right. So as mentioned, if you're using your iPad for Zoom, just stay on Zoom and look at my shared screen. All right, now we will start from the test for cations because I guess that is where it gets more confusing. And this you realize is really crucial because you need this to do the flowchart questions. Now, the first key concept here really is that to test for cations, you add either sodium hydroxide or aqueous ammonia. Now, sodium hydroxide contains OH minus ions, and so does aqueous ammonia because aqueous ammonia is an alkali. So it will produce OH minus ions when it's dissolved in water. Now, how is this OH minus important? Because when you add NaOH or aqueous ammonia in, you see a precipitate forming. The precipitate, as stressed during lesson, is always the metal hydroxide. Whenever you add NaOH or aqueous ammonia, the precipitate is always the metal hydroxide. For example, we go to copper 2. How do you prove that a solution contains Cu2 plus ions? One way is to add aqueous NaOH, dropwise first, then in excess later on. So you will form a blue precipitate when there is Cu2 plus. So what is this blue precipitate when you add NaOH? This is copper 2 hydroxide. So the precipitate is always the metal hydroxide. In this case, copper 2 plus. So copper 2 hydroxide. All right. So you should already be familiar with a few things. One, the color. Copper 2 plus should be easy because it's blue precipitate. And you should be familiar with whether it dissolves in excess NaOH, whether it dissolves in excess ammonia or not. So you realize that for Cu2 plus, it doesn't. It is insoluble in excess NaOH. However, it dissolves in excess aqueous ammonia to form a deep blue solution. Finally, you should be familiar with this writing of ionic equations for the formation of precipitate. Okay? Now, there is no substitute to studying this, and one good way really is to continuously do practical so that you learn these things. But actually, I would recommend that most students, before the practical, you need to read through this and perhaps write it out a number of times. All right. Next, Fe2 plus. The color associated with Fe2 plus is green. So when you add NaOH or aqueous ammonia to it, you form a green precipitate. This green precipitate is iron 2 hydroxide. The 2 is important because iron has multiple ions that it can form. All right, so iron 2 is just one type of iron ion. Okay, so the green precipitate is iron 2 hydroxide. Okay, and iron 2 hydroxide precipitate is insoluble in excess NaOH and aqueous ammonia. Then we move on to iron 3. Iron 3 is Fe3 plus. Fe3 plus forms a reddish brown precipitate. So the color associated with Fe3 plus is reddish brown. Okay, so learn the colors and also learn whether it's soluble or insoluble in excess NaOH and ammonia. Okay, I know it takes time. That's why I've segmented the notes as such. The first 3 ABC here, copper, iron 2, iron 3, these are colored. So they are easier to learn. Okay? Now, I'm not sure if Mr. Lee went through this, but let's go through this now as well. Now, you will realize that that day in the lab, I mentioned that whenever you see a green precipitate, iron 2 hydroxide, the green precipitate, you need to work fast. Why do you need to work fast with iron 2? Does anyone recall? What's the reason? You cannot dilly-dally. Why? Okay, let's ask someone. Okay, let's ask Junwei. Okay, Junwei, why must we work quite quickly when we have iron 2 involved?
Because the iron 2 will oxidize to become iron 3.
Okay, so the idea is the moment iron 2 is exposed to air, it can be oxidized by oxygen in the air. When it's oxidized, it means that it goes from iron 2 to iron 3. Fe2 plus becomes Fe3 plus. So you can see that there will be color changes happening if you are too slow. The green precipitate will slowly turn reddish brown. All right, Ken? So let's maybe write it down later. Iron 2 to iron 3 can be oxidized by oxygen in the air. So it's oxidized by oxygen when left to stand or left to expose in air. Ken? So this is something you need to take note of. Next, I think I mentioned in the lab that day, and you also saw it, the iron 2 hydroxide green color is not like a leaf kind of green. It is quite dirty. I think Angeline described it correctly, which was algae-like kind of green. Okay, so actually, when you go to A level, you will learn that there's a description for this. It's called dirty green. But for O level, we can just say green is fine. Okay, for iron 2. Now, another thing about iron 3, most students expect to see a reddish brown color. Yes, the precipitate is indeed reddish brown. However, okay, that is because it's a solid precipitate. How about iron 3 plus ions in aqueous solution? Let's say if this was aqueous, will it really look brown every single time? The answer is no. Now, it's good to also take note, if it's an aqueous solution, you should know by now, aqueous means dissolved in water. Solutions can either be concentrated or dilute, right? So similarly here, if I dissolve Fe3 plus in water, for example, iron 3 chloride, I dissolved it in water, I can make either a concentrated solution of iron 3 chloride, or I can make a diluted solution of iron 3 chloride. Do you think the colors will look the same exactly? I think the answer is no, right? Okay, I'm sure you have an experience like that. If you make, let's say, concentrated tea, the color looks darker than if the tea was diluted, right? So similarly, the same principle applies to solutions. Fe3 plus is supposed to be reddish brown, right? However, very often, if it's a diluted solution, it actually looks yellow in color. Okay, so when you do the flowchart questions, you will realize that there are some questions where they put yellow solution. Yellow solution is actually Fe3 plus, just as dilute. All right, so it's a bit like, okay, for lack of better comparison, urine. All right, urine when it's very diluted is very pale yellow. Okay, so dilute Fe3 plus solution is yellow. So when is it actually reddish brown in solution? When it's concentrated. So a concentrated solution will look reddish brown. And that also explains why the precipitate looks reddish brown, because precipitates are solids. So the solids are dense and condensed, all right? They're very dense. As a result of that, they will look brown, all right? Ken? So up to this stage, colored precipitates. No questions, right? Are there any questions that I can answer at this point? Just unmute yourself and ask for these three. No? Okay, don't worry if you didn't get it down in your OneNote. Later, you can go to content library and take it down, okay? So importantly, please try to get the notes that are just written down in red, because I think those are helpful whenever you do practical or flowchart question. Okay, so now we move on to the next page, which I think Mr. Lee went through, so don't need to copy anything, right? These are the confusing ones because these are the cation ions which give you white precipitate. Calcium, zinc, aluminium, lead. All right, so they are all white precipitates. The only difference, number one, is whether they dissolve in excess. Number two, okay, whether they form a precipitate in the first place or not. Good example, calcium, Ca2+. Ca2+ forms a white precipitate when you add a few drops of NaOH. The white precipitate is, of course, calcium hydroxide. So as you can see, the precipitate calcium hydroxide. All right. Now, calcium hydroxide is a white precipitate and it's insoluble in excess NaOH. Now, for calcium, if you add ammonia, you will not see a precipitate. So that's a good way to tell it's calcium, because calcium doesn't form a precipitate with ammonia. It only forms a white precipitate with NaOH. Then we move on to zinc and aluminium. Now, you notice that zinc and aluminium are easily confused because you realize that both form white precipitates with NaOH and ammonia. The only difference is, for zinc, the white precipitate can dissolve in excess ammonia, whereas for aluminium, the white precipitate is insoluble in excess ammonia. All right, so this is where you need to learn. Zinc, the white precipitate, zinc hydroxide, can dissolve in excess NaOH and ammonia. So we can of course write it down. Excess NaOH, dissolve. Excess ammonia, also dissolve. For zinc. For aluminium, excess NaOH, the white precipitate, which is aluminium hydroxide, will dissolve. But if I were to use excess ammonia, no dissolve. It's insoluble in excess ammonia. So excess ammonia is actually a good way to differentiate between zinc and aluminium ions. Okay? Can? Now, so the question, as I also answered in the lab that day, why is it that zinc and aluminium hydroxide precipitate will dissolve in excess NaOH? What makes zinc, aluminium, and lead as well so special that they can dissolve in excess NaOH? Rishi, do you recall what makes zinc, aluminium, and lead so special that they can dissolve? What is something that they have in common?
I forgot.
Okay, there's one term, starts with A. Zinc, aluminium, and lead, they are examples of?
Amphoteric oxide.
Yes, amphoteric. They form amphoteric oxides and hydroxides, meaning zinc, aluminium, and lead hydroxide, they are able to dissolve in acid as well as dissolve in base, like NaOH. All right. Now, lead, you don't do in the lab. Lab not in practical because toxic. But you need to know for theory. Now, lead, you will realize, is the same as aluminium. Excess NaOH will dissolve. But excess ammonia doesn't dissolve. So now comparing, if I zoom up slightly, you realize that zinc dissolves in both excess NaOH and ammonia. Aluminium and lead, they only dissolve in excess NaOH, not ammonia. Reason for that is because ammonia is a weak alkali. It's a weaker alkali than NaOH. So clearly, if I want to differentiate aluminium and lead, I can't use ammonia because both will give me the exact same observations. That is, both aluminium and lead will produce a white precipitate, and the white precipitate is insoluble in excess ammonia. So you cannot use ammonia to differentiate between aluminium and lead. All right. And there comes this monstrous flowchart. So this is just a summary, which I'm sure Mr. Lee went through that day. If you have calcium, zinc, aluminium, and lead, how do you differentiate them? First, you add aqueous NaOH dropwise until in excess. Why? Why do you add NaOH first? Because we already know zinc, aluminium, and lead forms a white precipitate that can dissolve in excess NaOH. Zinc, aluminium, and lead are amphoteric. So because they are amphoteric, they will dissolve in excess NaOH, whereas calcium forms calcium hydroxide, which is basic. So it will be insoluble in excess NaOH. So by adding NaOH, I can already sieve out calcium. I differentiate calcium away already. So now, The mixture contains zinc, aluminium, lead remaining. How do you differentiate between them? Adding ammonia. Aqueous ammonia dropwise until it is in excess. Why? Because we also know zinc not only dissolves in excess NaOH, it can also dissolve in excess aqueous ammonia. So if it dissolves in both NaOH and ammonia, it's zinc, which leaves you with just aluminium and lead. And as mentioned, you cannot use ammonia alone to differentiate aluminium and lead. I believe Mr. Lee went through that day. To differentiate aluminium and lead, we add potassium iodide. Aqueous potassium iodide can differentiate between aluminium and lead. All right. If there's no reaction with potassium iodide, that means it's aluminium ion. If, however, there's a yellow precipitate formed, this is lead. Okay, so lead, Pb2 plus, will form a yellow precipitate when you add potassium iodide in. Okay, now what is this yellow precipitate? Actually, this yellow precipitate is lead 2 iodide. Lead 2 iodide is insoluble in water, it's an insoluble salt, so it will precipitate out and it's yellow in color. All right, so you can see, actually the video is right on the right hand side, and that's why if you are in OneNote, please view the videos on the right hand side of this section. Okay? Ken? So this is actually how you distinguish between aluminum and lead. Okay, at this juncture, calcium, zinc, aluminum, lead. Questions? Please feel free to ask. There's no question too basic. No? Well, no means we can do the flow chart, is it? All right, so last one. Ammonium. Now, ammonium is a commonly forgotten cation ion. It's positive, okay? Ammonium is a positive ion, so it's a cation ion. NH4 plus. Okay, the charge is +1. Now, how do you test for ammonium ion? You have actually learned this under acids and bases. You have learned that base plus ammonium compound will give you ammonia gas. So we make full use of that. To test whether something contains ammonium, we add NaOH and then gently warm it. Why? NaOH is a base. Base plus ammonium compound gives you ammonia gas. So if it contains ammonium, add NaOH, then you warm it, you should produce ammonia gas, which turns moist red litmus paper blue. All right. Now, you have not gone to the lab to do a full exam practical, but ammonium ion test is actually very, very common in QA practicals. Okay, and how do you know that it's an ammonium ion test? How do I actually know that it's ammonium ion? Clues like adding NaOH and gently warming it tells you that it's an ammonium ion test. So the examination instructions, as you do the practical, you have self-instructions to follow, right? Step 1, do this. Step 2, do that. Inside the steps instructions, they will actually write down add aqueous NaOH, then gently warm it. So it should come into your brain, okay, add NaOH, gently warm. This is a test for ammonium ions, which should produce ammonia gas. Since it produces ammonia gas, I should prepare red litmus paper. Okay? So you need to have this sense of what is going on in QA. From the instructions, NaOH, gently warm, can you be a detective and piece it together that this is actually a test for ammonium ion? Okay? That is the skill that you need. And that's what we are trying to develop right now. Okay. Now, so that is it for the cation ions. The cation ions are the most difficult because there's a lot of them and you need to learn them by heart. When I say learn them means what? You need to learn Number one, the observations, whatever is there, word for word. Number two, you need to learn how to test for the cation ions. Add NaOH drop-wise, then in excess. Add aqueous ammonia drop-wise, then in excess. All right. Now, the anions are slightly simpler, but may be confusing for some of you as well. Anions are negative ions. For example, chloride, iodide, sulfate. These are negative ions, right? A trick to learning this is to learn the test itself. Chloride and iodide is tested for using silver nitrate solution. All right, so when you see silver nitrate in your flow chart, in the exam question, or in the practical instructions, you must immediately know, okay, I'm either testing for chloride or iodide. All right, you got to link the two together. Silver nitrate is a test for chloride or iodide. Can? Now, if it's chloride, what would you see? You will see a white precipitate formed. What is this white precipitate? It is silver chloride. Now, silver chloride is Ag plus, Cl minus, so it's AgCl. So I think Mr. Lee gone through this that day. Okay. Now, silver chloride, AgCl, is a white solid precipitate. Whereas if it's iodide, the precipitate is yellow because the yellow precipitate is silver iodide. Okay. Okay, so I believe that day you wrote this in class already. Now, you notice a pattern. Just now, actually, okay, Rishi, I'll come to you. Just now, there's a pattern, right? Actually, iodide, iodides. Just now, the lead-2 iodide was also yellow, right? Precipitate. Silver iodide also yellow. So learn the patterns. Iodides, when they form precipitates, are actually yellow in color. All right. Yes, Rishi, you raised your hand just now.
So why do we need to add dilute nitric acid?
Okay, so that's another important question, right? How come cannot just add silver nitrate straight away? Why must I add nitric acid first, then aqueous silver nitrate, right? Now, I'm sure you realize over here, the reaction is precipitation. You're forming a precipitate. So the type of reaction, the name of reaction is called precipitation. Precipitation occurs when the salt is insoluble, precipitates out. Now, you got to think in your head, besides silver chloride, is there any other silver salt that is insoluble? Many, there are other possibilities, right? One possibility is actually carbonate. Silver carbonate is also insoluble in water. If you recall the rule, the solubility rule that we learned last chapter, all carbonates are insoluble in water except SPA. What does SPA stand for? Let's ask someone. Okay, let's ask Andre. Andre, what does SPA stand for?
Sodium, potassium, and ammonium.
Correct. So you think about it, silver is not SPA, no? That means a silver carbonate is insoluble, right? So if there's carbonate with chloride, the carbonate can precipitate out as silver carbonate. Is that what you want? No, we only want silver chloride. We don't want silver carbonate to precipitate out. That's why we must add nitric acid first. By adding nitric acid, we are actually reacting away any carbonate ions. And the purpose of reacting away carbonate is so that it will not precipitate out. Okay, when it precipitates out, then you got a problem, because now you don't know if the precipitate is silver carbonate or silver chloride. Can't tell. Okay, so we add acid so as to react away any possible carbonate ions in solution so that the carbonate will not precipitate out. Okay, can? So Rishi, remember the precipitate we want is silver chloride. We don't want silver carbonate, so you must react away the carbonate first using acid. Okay, so hopefully remember acid plus carbonate from salt water and carbon dioxide gas. Okay. Now, so Rishi's question is actually good because you realize for sulfate tests, we also add nitric acid first. The reason is exactly the same, which is I don't want the carbonate to precipitate out, so we add acid first to react away any carbonate ions. All right, so next we want a sulfate test, also quite similar sounding, right? Similar sounding, but the chemical different. So to test for sulfate, we use barium nitrate. Just now, chloride iodide, we use silver nitrate. Now sulfate, barium nitrate. So you form a white precipitate. The white precipitate is barium sulfate. Okay, so write the equation. Okay, can? Now, learning this is important. As you can see, I again group these together. A, B, C is all precipitates. Just that chloride and iodide, to test for it, we add silver nitrate. Sulfate, test for sulfate, barium nitrate. So you got to link. What do you add? I added barium nitrate. Barium nitrate means testing for sulfate. You got to link it this way in your head. And when you revise, that's how you revise. Linking things together. Being able to identify what am I testing for? I am testing for sulfate because I'm adding barium nitrate. This is a particularly important skill because later on when you go to the lab, the practical instructions will just say add barium nitrate. They will not tell you whether it's a test for sulfate or not. You are supposed to know it's a test for sulfate because it says barium nitrate. Okay. Now moving on, carbonate ion, nitrate ion shouldn't be too difficult. Carbonate ion is easy because it's just adding any acid. Add acid and you form CO2 gas, that means it's a carbonate. Because CO2 gas must come from a carbonate. All right, that's the only way to produce CO2 in the lab. Typical experiment involving a carbonate. Nitrate is a new test, so I advise you to learn it. You got to learn it now. Nitrate ion is to add aqueous sodium hydroxide and aluminium and then gently warm. Now the aluminium can be in the form of aluminium foil. Okay, so typically we will say aluminium foil, but of course you could use aluminium powder as well. It works the same way. So aqueous NaOH, aluminium, and gently heated or warmed. This is a nitrate test. Now, as chemistry students, you also need to learn how to compare with other similar sounding tests. Don't you realize the nitrate test sounds very similar to an ion previously? So what is this similar to? Let's ask someone. Jamin, nitrate ion test sounds very similar to another ion just now. What was the ion just now? Is Jamin there? Jamin, hi. This nitrate ion test sounds very similar to an ion just now. Where you added NaOH as well and then warm it. Jamin?
Oh, wait. I found it, I think.
Which ion just now did we talk about?
Is it ammonium ion?
Yes. Ammonium ion is almost the same, right? Add aqueous NaOH, then warm gently. So what's so special about nitrate? What did we add? What's a special ingredient? The special ingredient that tells you the nitrate test is aluminium. The moment you read aluminium foil, aluminium means it's a nitrate test. Okay? This is how you learn things, to memorize things better. You look at what's the special attribute, the special characteristic of the test. Nitrate ion test requires aluminium. Okay? So you should see ammonia gas being formed. You can't see with your eyes, you have to test for the gas. How do you test for ammonia gas? You place a piece of moist red litmus paper at the test tube, and then the gas will turn moist red litmus paper blue. Can? Now, so as you can see, there's no substitute to learning this. And I'm sure that day in the class, Mr. Lee went on to the next part, which is how to do this kind of question. Now, this is called a flowchart question. It is not common in pure chemistry. It's not common in pure chemistry. All right, combined science will have one of these every single year, and it's like 7-8 marks. So all the combined science students know this, and that's why just now you saw my Teacher's Day gift from the Sec 4. That student literally drew out me in the lab saying QA is important because I literally scream this in their face every single year. QA is important for combined science students, and the combined science question looks like this. This is a combined science question, not a pure science question. Does it mean that pure science will never have flowchart questions? No, it doesn't mean you will not have. That means you could still have this, just that it's not every year. Or they could test you QA in other forms. But nonetheless, there is no substitute to learning QA well, because it could appear in practical and theory, and it will appear in both practical and theory. Okay? So what does it mean to do QA well? First, you must learn the tests and observations for every single ion, every single gas. And you got to learn it the way I told you just now. When you see aqueous barium nitrate is a test for sulfate. You got to link it together like this. All right. Now, when you are faced with this kind of flowchart questions, it's like you being a detective. Where do you start? What are the clues? Can you piece the clues together to get the whole story? So, which clue do you start with first? Okay, I'm sure Mr. Lee mentioned good chemistry students must start with the gas first. That means you identify the gases first. Then you look at colors. And finally, you look at the solubility. Of course, solubility of the precipitates. So let's use this good chemistry student GCS framework to solve this. First, we start with the gas. Obviously, in this flowchart, the only gas is S. S is a colorless gas. And you are told that gas S, when you add aqueous calcium hydroxide, it forms a white PPT. Calcium hydroxide, another name for it is lime water. Meaning gas S is bubbled into lime water to form a white precipitate. So S is carbon dioxide. Since we know that S is carbon dioxide bubbled into lime water, the precipitate formed in lime water is called calcium carbonate. So as you can see, just by looking at the gas alone, I've scored 2 marks already by identifying S and V. Okay, now besides that, if you listen to class, you know carbon dioxide gas come from where? It must come from a carbonate. That means S came from where? S, which is carbon dioxide, came from P, right? P formed S, right? So P is the carbonate. I don't know what carbonate it is. It could be zinc, calcium. Don't know. Don't know, put a blank in front of it first. Come back to it later because you have not seen all the clues yet. You don't know whether zinc, copper, calcium, iron, can be anything, right? We don't know, leave blank first. But at least you must write down it's a carbonate because only carbonates form CO2 gas. All right. Now, we have exhausted what we can do already. So now let's move on to the next one. C, color. Gas, then color. What's the color? It's white. So white tells you what? White tells you, that means it's not iron 2, not iron 3, not copper 2, right? Because these ions that I just mentioned won't be white. So what is going on? It's white. It's white precipitate when I add aqueous sodium hydroxide until excess. What does this actually mean? This means that the white precipitate is insoluble in excess, right? If it's soluble in excess NaOH, they would have written a white precipitate and dissolved in excess NaOH. What? The fact that they just wrote white precipitate means it didn't dissolve in excess, right? If it dissolved in excess, they would just write a colorless solution is formed. Full stop. But it's not. Right? They wrote white precipitate form. That means T immediately insoluble in excess NaOH. If you study, oh, it's not zinc. Oh, it's not aluminum. Oh, it's not lead. It's calcium. Right? So now you realize it's calcium hydroxide. That means R contains calcium 2+. Clearly, this also means that P contains calcium 2+. The metal here is calcium. And R must be calcium something, don't know what. Can be calcium chloride, calcium nitrate, don't know yet. Find out later. Can? So finally, we look at the next gas. I missed out one gas, I'm sorry, just now. There was gas U. This is ammonia gas, right? Gas U is ammonia gas because it turns moist red litmus paper blue. Okay. Now, very important, add aluminium powder is a test for nitrate. So if you listen to me just now, aluminium foil, aluminium powder, aluminium. When you add it in, it's used to test for nitrate and you get ammonia gas formed. This means that immediately you know that R is calcium nitrate. And there it is. I've scored almost full marks. The last one is acid Q. Acid Q, to form a nitrate, what acid do you add? Nitric acid. Now, I hope you realize by now, what I do is I look at possibilities and I narrow down the possibilities. You do not broaden the possibilities. You narrow down the possibilities. Like I say, it cannot be copper, it cannot be iron, it cannot be this, cannot be that. Okay? You should narrow down, not broaden. Now, what do I mean? Most students find flowchart very hard because they keep thinking of different things. There's no need to. You won't suddenly have chloride in this question, no. If it's nitrate, it's going to be nitrate throughout. If it's calcium, it's going to be calcium throughout. You are never going to have calcium in P, then suddenly somewhere else copper too. Cannot. Unless there's really copper added in the equation, in the flow chart. All right, so you should narrow down possibilities. If it's calcium throughout already. If it's nitrate throughout already. You will not suddenly have chloride coming out from nowhere. Can? So the trick is to use the GCS, good chemistry students use gas, color, solubility of precipitates to solve the flowchart. And the next trick is narrow down the possibilities. Do not broaden. Do not start thinking of other things that are not there. All right. And we are not going to torture you, okay? If it's nitrate throughout. If it's calcium throughout. It's not going to suddenly change. All right. So herein, let's go to the flowchart questions, which I think you have it in hard copy. That's the homework that you're supposed to do. You might think I'm crazy giving so many questions, but let me just say this. I gave this to my Sec 406 combined science during the June holidays when I was overseas in Thailand and I Zoom consult them like this. There's no substitute to doing this. They learned a lot from this. They went through this, suffered through this, but through this, they also became more familiar with QA tests. All right. Once you are familiar with this, actually QA is a sure full marks one now. So this prelim, as I flip through my 406 combined science, most of them scored full marks, if not close to full marks for QA. And that means a lot. For them, it meant like 8 marks out of 65 marks that they scored just on one question. Okay. Now, I'm not going to go through every question. My purpose today is not to go through every question and give you an answer. You need to learn how to do it. Okay. So I'm just going to show you, then I'm going to show you one question only. How to start. After that, okay, I will really leave it up to you to do yourself. I'll be online. As you do, you can ask me questions. All right. Now, let's do question 2. Has Mr. Lee done question 2 in class? Maybe someone can respond to me. Has Mr. Lee done question 2 in class? No.
No.
Andre says no. Jamie, no, right?
Yes, no.
No. Okay, let's go to question 2. Question 2 fully illustrates what I mean by GCS. Good chemistry students. You must start with the gas. And it's quite clear-cut what is the gas, right? It's gas R. Gas R is a colorless gas and you are told it's bubbled into lime water. Isn't this a straight out giveaway? That means gas R is what? Let's ask someone. All right, Lucas, what is gas R? It's bubbled into lime water. Lucas is here, right? Thought I saw him just now. Lucas, are you there? Lucas, are you there?
Yeah.
Okay, so what is gas R? It's bubbled into lime water. Lime water. It's a keyword you link with what gas?
Carbon dioxide.
Yup, that is correct. Okay. Now, you notice Mr. So will write down things in the flowchart one now. I will highlight keywords like lime water. I will write things down. Once I know that R is CO2, I'm just going to write it down in the flowchart. You should do that. Your flowchart shouldn't be clean. If it's clean, there's no annotation, something is wrong. It's like those lead students. Lead students, you all study lead, right? If your lead text, your book, your poem has no annotations, something is wrong. All right? So similarly for QA, you must have annotations. Please write down CO2, okay, in the flowchart. Not just in the answer. Actually, I'm not so interested in the answer. No, I'm really interested in the flowchart, what you write, and what you underline or highlight, okay? So yes, R is CO2. It's bubbled into lime water. It forms white precipitate T. So let's ask someone. All right, Jing Kang, what do you think is white precipitate T formed in lime water?
I don't know. I put calcium carbonate.
Yeah, it's correct, calcium carbonate.
Yeah.
It's a standard answer, right? CO2 plus calcium hydroxide plus lime water, that is calcium carbonate precipitate. Okay, so have more confidence in yourselves. Calcium carbonate is correct. So we're going to learn this, right? We're going to remember this, right? Yes. Okay. Okay, by the way, you just got 2 out of 5 already. No, wow. Within like 10 seconds, you can get 2 out of 5, right? Just based on gas test. Obviously, that's the only gas left. There's no other gas. But before we move on, important. I already told you, right? Carbon dioxide gas must come from a what? Jet. Carbon dioxide gas must come from a
Carbonate.
Yes, that means P, because R came from P, right? R started from P, so P is a carbonate. Don't know what carbonate, put blank. I should see y'all doing this, You don't write down carbonate means you don't even think about it. So P must be something carbonate lah. Can be zinc, calcium, I don't know, aluminium. Don't know yet. Let's try. Okay. Now the next thing we should work on is color. Unfortunately or fortunately, the color is white precipitate. But you have this yellow solid Q turning white. Ooh, never learned before. Okay, this one you have never learned before, and it's not in the notes. But based on the later evidence, never learned before, skip first, right? So I don't know what is Q, never learned before. But I can do U what? U is a white precipitate that's soluble in excess aqueous ammonia. It's soluble in excess ammonia. It's white. What is this? Soluble excess aqueous ammonia. What can dissolve in excess aqueous ammonia? So you can see this is where studying comes in, right? If you know which ones will dissolve in excess ammonia, immediately the answer is easy to get. Okay, so you can refer to your OneNote now. Look at which cation will produce a white precipitate in ammonia, and the white precipitate will dissolve in excess aqueous ammonia. Okay, Audric, what is white precipitate U?
Should be zinc.
Zinc, right? So you must study until you get to the point that you know, oh my God, this is Zn2 plus. Oh my God, it's Zn2 plus cause it dissolves in excess aqueous ammonia. But is the answer just Zn2 plus, Audric? We are asking for the precipitate though.
Zinc carbonate.
Zinc carbonate. U is zinc carbonate. When you add ammonia, the precipitate is not the carbonate, the precipitate is the
Ammonium.
ammonium, really? Ammonia, NaOH, when you add, the precipitate is always what? Audric, the precipitate is always the not carbonate, not ammonium.
Hydroxide.
Yes, that's why we make you all write the equation, right? The precipitation always hydroxide, right? So U is zinc hydroxide. Okay. Now you will see that in this school, our worksheets used to write ammonium hydroxide in the past, add aqueous ammonium hydroxide. I think I mentioned this before in the acids and bases. Aqueous ammonia, another name for it is actually ammonium hydroxide. All right, because it's an alkali that produces hydroxide. Then you must be wondering, how come Mr. So is so cruel? Don't want to put ammonium hydroxide. Isn't it easier? Then we will remember it's hydroxide, what? But I deliberately don't do that. As you can see, this is other school prelim paper. No school will write ammonium hydroxide in the exam question. So you must get used to it. When you see aqueous ammonia, you must know there is OH minus ions. And the precipitate will be the hydroxide. Okay, wow, Stella. Okay. Can? Clear? So when you add aqueous ammonia, it's the same as adding aqueous NaOH. The precipitate is the metal hydroxide. Okay? Can? Don't think of like other things already. It is the hydroxide. All right? Now, with practice comes perfection. Then you will be more familiar. Add aqueous ammonia, reflex it action. Instinctively, you know it's the metal hydroxide. Okay? Now, this is important. So now you have established zinc. So are you going to suddenly have copper in this question? No, right? Are you going to suddenly have iron 3 in this question? No, right? Which means immediately P is zinc carbonate, right? It can't suddenly be something else, you know. If you have established that the main character here is zinc, it's going to be zinc. And true enough, it is zinc carbonate. All right. Can? So you can see the value of making annotations in your flowchart. When you started with just gas, carbon dioxide, so easy, right? Bubble into lime water means carbon dioxide. Then you realize carbon dioxide must come from a carbonate. So P is a carbonate. Just that I don't know what carbonate. So I leave a blank first. Then you go on to color. Oh, it's white. Oh, solubility is soluble in excess ammonia. Then as Audric told us, is zinc. Therefore, P is zinc carbonate. It's not going to suddenly, U is zinc, then P is something else. Cannot be. It must be the same thing. That's called narrowing possibilities. All right. Which means that Q can't suddenly be something else, right? Q must be zinc something, right? Just zinc what lah, right? So this is where you use a bit of chemistry. Now I'm sure you know by now what is zinc carbonate. Zinc carbonate's formula is ZnCO3. Now P is zinc carbonate, ZnCO3. You heated ZnCO3 strongly to form two things. One is CO2, right? When zinc carbonate was heated strongly, it forms CO2 gas. You have already identified that. So what do you think is the other thing Q? What's Q? What do you think is left behind? So CO2 came out from ZnCO3. What is left? So you started with ZnCO3. CO2 came out already. So what is left?
Is it zinc oxide?
Isn't it zinc oxide? Yeah, it is, right? ZnCO3, CO2 removed already. So what are you left with? Zn and O. ZnO, zinc oxide. All right, not convinced? Try writing the equation out lah. I mean, if you're not convinced, but in the exam, of course, no time to write equation, right? And it works, right? This equation works, right? It's balanced. Now, this is actually, heat strongly, actually, this is the decomposition of the carbonate. So later on, not now, later on when you go back to your OneNote, you realize under the notes, under the test for CO2, I actually wrote down which reactions produce CO2. There are only two reactions that produce CO2 in the lab, more or less. Acid plus carbonate, as well as decomposition of carbonate. So this is decomposition of zinc carbonate. Decomposition will produce CO2 gas as well as the metal oxide, which is zinc oxide in this case. Now, zinc oxide is very unique. Zinc oxide is white, but only when it's cool. That means at room temperature, like right now, if you have zinc oxide in the open, now it's cold, it will be white. However, you are heating it strongly, right? Just now you heat the carbonate strongly. Heat strongly means hot. When zinc oxide is hot, it's yellow. That's why it's written here, yellow solid Q turns white when cool. This is a giveaway that is zinc oxide, because only zinc oxide will behave this way. Okay, so I put an exclamation mark there because you got to learn. This one you will learn through practical lah. So my Sec 4s, they learned it through practical, and I screamed this in their face many times already, so they know. Zinc oxide is one of those interesting, unique solids that you must know because it has a different color depending on temperature. It is yellow when hot, white when cool. Okay. Now you are encountering it for the first time. I'm not expecting you guys to memorize this. Okay, you don't have to memorize this immediately, but it's very useful. The moment you know this, you are able to finish practical in like 20 minutes. I saw my 4NA SBB student. Okay, I mean, this was actually their prelims. All right. I saw that my 4NA SBB student can finish the entire practical in 20 minutes and have 10 minutes to spare just to write up and check his work, which means that he has 1 hour left to do physics practical, but combined science, the practicals together. All right. He finished chemistry in 30 minutes, seriously. And his chemistry is that whatever he wrote was more or less correct. Yeah. Okay. So how did my 4NA SBB student get there? Through learning these little things along the way. So learning little things like, oh, carbon dioxide comes from carbonate is important. Next, you should know in this case, heat strongly means decomposing the carbonate. Decomposing the carbonate will form the oxide. And I know it's zinc oxide immediately because it's yellow turns white when cooled. Yellow when hot, white when cooled. All right, so that leaves us with the very last one, which is S. I'm sure you can work out by now. S is not going to be calcium something. It's not going to be iron 2 something, because this whole question is about zinc. But zinc what though? So you're going to read at the previous line. S came when Q reacted with dilute sulfuric acid. Dilute sulfuric acid gives you what? So it must be zinc what? Sulfate, right? So S is zinc sulfate. Okay, and that's how you solve the entire puzzle. Can? Now you realize the annotations are really important. Without the annotations, it's going to be very, very difficult for you to do. Okay, and I hope you apply these skills of annotating in other subjects like A-Maths as well. I mean, side conversation. I find that many students, even my ex-students, when I taught them A-Maths in school, they tend to stare at the A-Maths problem for very long without even writing anything out. I really wonder how they do that, because without even writing out any working, how do you expect to get a solution for A-Maths? And remember, A-Maths, your solution to a 5-mark question could be like one entire foolscap page, right? So without even writing something out, like any working, right? You write the working out, maybe you'll realize that, oh, it doesn't work. Therefore, let's try something different. But you must first have written it out. You cannot expect to do A-Maths without annotating. Similarly, QA is the same. You cannot expect to do this kind of question without having it being messy. You must have had written out a lot of annotations to help you do it. Of course, don't just anyhow write anything down. Make sure it's logical. How do you ensure it's logical? Like I said, go in the order. Good chemistry students start from the gases first. If you started from carbon dioxide in this question, I can guarantee you will almost certainly get like at least 4 out of 5. But if you didn't start from carbon dioxide gas in this question, you are going to have huge difficulties because you wouldn't know where to begin. It's just going to be overwhelming. Okay, so I hope you use these skills very well. Annotations, good chemistry students do the gases, then colors, then solubility of precipitates. All right. Ken, so this is how you do a flowchart question. Now, I am not going to continue the consult from here because I actually want you to try the questions, but I'm going to remain online for the next 25 minutes or so. So if you want to remain online and try the questions out in this assignment and ask me if you have any questions, I'll be more than happy to answer you. Okay, but remember, there is no substitute to learning the tests and observations for ions and gases. That means you got to memorize them. Okay? And remember, when you memorize smart. Try to link things together. Link what? For example, lime water is linked to carbon dioxide. Silver nitrate is linked to chloride ions. Aluminium foil is linked to nitrate ions. Linking things together helps you memorize things faster and more effectively. Secondly, remember you need to use the GCS framework to work things out. Narrow the possibilities, don't broaden, narrow. Thirdly, annotate, like what I did. Okay, so with that, okay, if you want to stay online to do the problems, then you can check in with me. I'll be more than happy to answer your questions. If not, okay, please enjoy your holidays. Okay, but also do my chemistry homework, okay? Have fun, but chemistry is fun, right? So you should have fun while doing chemistry. Okay? So if you want to stay online to do the problems, I can always check in with you on the answers as well. If not, you are free to leave. All right, thank you. I will stop recording here as well.
Thank you, Mr.